Our first video worked through the computations to compute a regression line. This second video is going to show us how we can use it for prediction, hypothesis testing, and how we can interpret the results. Our general regression line equation that we saw in the last video shows us that we have a predicted y or dependent variable score that's based on our independent variable multiplied by the slope with the intercept added on. The example that we worked looked at our high school GPA as an independent variable to predict, so I'm going to put the little hat on it, our college GPA as a dependent variable, and that we would take the high school GPA, multiply it by the slope, and add on the intercept. In general, we can only use these predictions within the range of the x-scores that we used to compute the regression line. So for instance, it would not be a valid use of this equation to predict the college GPA for somebody whose high school GPA was 1.0, because we did not have any data in that range. We only know that we had a linear relationship for the part of the scatter plot we could observe, and seeing as we didn't have anybody in that very low range, the graph could, if there were people like that, drop off dramatically, and it would not be a suitable line to represent that part of the equation. So we could look at a GPA of 3.0. We had plenty of people that were between 2.5 and 3.5, but we did not have anybody at exactly 3.0. If we did have such a person, we would plug in the 3.0 and predict their college GPA by multiplying that by the slope, adding on the intercept, and saying that the 3.0 high school student would be predicted to be a 2.83 college student at the end of their first year of college. And this makes sense. The high school GPA that we began with, 3.0, was slightly below the mean, which was 3.14, and the predicted college GPA is slightly below the mean of college GPAs, which was 2.93. As we saw in the last video, regression is the method for determining the best fitting line through the data, and the criteria that's being used is the predicted value minus the actual value, and that whole thing squared for each of the data points. And the regression line minimizes that total squared error. And we've heard that phrase before about total squared error, and we've seen it when we did analysis of variance, and we could talk about a sum of squares that was due to error. So I think you may be beginning to see that our regression and our analysis of variance have a lot in common. In the first video, we looked at the deviation scores of points relative to the regression line, and we saw how that deviation score could be squared, and it would give us the error of prediction relative to the actual data points. Our null hypothesis, if we were having a null hypothesis, would be that all of the data points, no matter their x value, were equal to the mean on the outcome variable, which was 2.93. So we could compute the errors around that mean by taking the squared differences and adding them up. And if you remember from our analysis of variance, that would give us a sum of squares total. All of the variability that we have in the y variable would be that sum of squares total. So part of what we can do with our regression line is to ask whether we have less error when we use the regression line to predict than we would have if we didn't have the regression information and had to just use the null hypothesis. So if our regression leaves us with a sum of squares error, and we also have the possibility of this total sum of squares, you can begin to see that we'll also have a sum of squares due to regression, and we'll be able to do some of the same type of analysis that we did when we were working with analysis of variance. Regression has a lot in common with correlation, which makes sense because the regression line is the linear relationship that our correlation variable was measuring. So I'm looking here at the data analysis tool pack, which will carry out the correlation analysis for me. If I take the entire range that has both of my variables, or if I had more than two variables, I could also make a larger correlation matrix that showed all of them. And I enter that range into the input range. In this case, I do have labels in the first row, so I let the Excel spreadsheet know that I have that. And when I click OK, it will produce for me this matrix that shows the correlations. And the value 6.683 is the strength of the correlation that we saw in the very first slide of the first video. Excel will not automatically create for me R squared, but it's easy to use the power function, we've used it before, to find out what proportion or percentage of the variance is shared between my two variables. This is something that we saw in the module on correlation. When I square my 0.68345, I get the number 0.467. And we're going to see that number come up from our regression analysis in just a minute. So we'll begin to see how these two approaches actually mesh up with each other. The coefficient of determination is the term that we used to describe the proportion of shared or predicted variability between our two variables. And in this situation, we saw that it was 0.467 on the last slide. We can also talk about the coefficient of alienation, which describes the unshared or unpredicted or error variability, and it's 1 minus the coefficient of determination. So in this situation, it would be 1 minus 0.467, equaling 0.533. So we can use this information to compute a standard error of the estimate for hypothesis testing, and the textbook goes about showing you how to do this, and it means we could also compute a sum of squares error. That sum of squares error takes us back to the perspective of the analysis of variance. If you remember a few weeks ago when we were studying ANOVA, we looked at the total variability in the dependent variable, and we partitioned it into two parts. One of them was a systematic part. In the analysis of variance, the systematic part were the differences between the groups, because we were looking at groups of people, and we said that any variability that happened between the groups was due to the treatment variable, but any variability that happened inside the group where they all received the same treatment was the unpredicted or the within groups variability that we called error. In our regression approach, we no longer have groups because our predictor variable is measured along a continuum, but with the same idea applies. The part of the variability in Y that is related to our prediction, in other words, how much better is our prediction with the regression line than it would be without it is the systematic component, and the part of the variability that's still not predicted, even though we're using the regression line, is the error. So again, we have a systematic component and a random component. In analysis of variance, we were looking at the differences between groups. With regression, we're looking at the difference between a prediction based on a regression line and a prediction based only on the mean of the outcome variable. As you expected, the data analysis tool pack does have a function for carrying out regression. The one thing to be very careful about is making sure that you do not mix up which variable goes in which location. Where it says input y range, that's my outcome variable, my dependent variable. In this situation, it's my first year college GPA, and I used a named range so that I would be sure to get the right variable. My independent or x variable goes in the other slot, and again I used a named range in order to help me make sure not to make an error. I told Excel that I had labels in my first row, and I don't need to do anything special with the rest of this except to choose either to use a new worksheet, or I could have selected to put in an output range on the same sheet. As soon as I click OK, I will get my results as we see on the next slide. After I've clicked OK, I get quite a bit of output from the regression part of the analysis tool pack, and we're going to look at it in different parts. The first thing I want to look at are the coefficients. These are the slope and the intercept that we computed in such great detail by hand when we were working with it in the first video. It's nice to see how quickly it comes out in this part of the tool pack, and as soon as I have those two pieces of information, I am able to write the equation for my regression line saying y equals 0.70389 times x, in this case the high school GPA, plus 0.7198, my intercept. This lets me know that my college GPA outcome variable will increase about 0.70389 for each 1 point increase in high school GPA. So the first thing we've been able to do is create the regression line equation using the coefficients. Some of the other elements of our regression output let us do something that's very similar to an analysis of variance. It's called an analysis of regression, and it gives us a test for the significance of the regression line as a prediction. It will look at the shared variability of x and y in the numerator and the variability due only to error or chance in the denominator, just as we had a systematic component and an error component when we were looking at the analysis of variance. So our systematic component is in the numerator and our error component will be in the denominator. This slide shows us the equations that we would use if we were having to compute this by hand. You'll notice that we have the coefficient of determination and the coefficient of alienation, each being multiplied by the total variability, the sum of squares total. On the blue side, where we're dealing with residual, this is our error or random component, and on the right hand side, where we're dealing with regression, this is our systematic or our regression elements. And with both of these we get a sum of squares, a degrees of freedom, and when we divide the sum of squares by the degrees of freedom, we get the mean square. Our analysis of regression test is completed when we have those two mean squares, the one for regression and the mean square for error. When we take those two mean squares and divide them, the regression on the top, the residual or error on the bottom, we get our F statistic. In our output, we can see that Excel or the Google spreadsheet with the Excel minor has already done that work for us. Here's our F statistic, and in addition to giving us the F statistic, it gives us the p-value, which, if you remember, we can compare to our alpha. Our usual alpha is 0.05, and when our p-value is less than 0.05, less than alpha, we can reject our null hypothesis and say we have a significant result. So when we use the analysis of regression, I'm able to say that this regression line gives me a better prediction than I would get by just using the mean of the outcome variable as my standard prediction, which I'd have to do if I didn't have an improved predictor. But just as we have in every single one of our hypothesis tests so far, if I find that I have a significant effect, I need to have a measure of effect size. For regression, our effect size is computed as capital R squared, a proportion of the variability in y that's predicted by x. So we have our total sum of squares, and out of that total sum of squares, some portion of it is the sum of squares that's due to regression. When I compute that fraction, I get my r squared. And you can finally see where this letter r that we've seen throughout the course originated. It was the r for regression, and it's the source of that letter r that we've seen when we looked at little r squared as the measure of effect size for t-tests. We looked at little r squared as the coefficient of determination when we were dealing with correlation. So we've seen that r squared several times. In analysis of variance, we had eta squared, but it was the same form of computation, a systematic sum of squares on the top and a total sum of squares on the bottom of a fraction. And as you expected, the r square is computed for us in our output from Excel. You'll notice that right below is a second number that in this case looks a little bit different, and it says adjusted r square. The equation adjusts for the number of independent variables, and it's not an appropriate number to use that adjusted r square when we only have one independent variable. But as we have larger numbers of independent variables, which would happen in an advanced statistics course, then the adjusted r square would in fact be a number that you want to have. In explaining the hypothesis test, the textbook looks at the standard error for the coefficient for the slope and computes a p-value for that coefficient. And that's in fact what happens when we get into multiple regression, which is where the textbook explains the hypothesis test. In the situation that we're looking at here, you'll note that these two p-values, the one for the overall f and the p-value for the coefficient for the slope, are identical, and that's because we only have one variable that's in the equation as a predictor. If we had more than one variable in the equation, the p-values would differ among the variables, and they would differ from the overall significance because they might have some shared variability or interaction among them. So with a simple regression, only one predictor variable, our significance for the entire model will be the same as our significance for our one variable. Our final task is to write up the results of our regression and in the process learn what to expect when we're reading regression results. The first thing to remember is that we're going to avoid mentioning the language about the statistical test. So I'm not going to write about a null hypothesis or rejecting a null hypothesis. I'm going to begin with a narrative sentence. I'm going to state whether the regression was significant or not, and regardless of whether it was significant or not significant, I will report the F-test results. If I did have a significant result, I have to say something about the slope, and I usually express it in terms of how much the dependent variable will increase or decrease for a 1 unit, or if the units are very small, I might even report for a 10 or 100 unit change in the independent variable. And again, if I had a significant result, I also need to say something about the effect size and then close with a narrative sentence. Let's look and see what that would be like for the data that we have been looking at so far. Usually for this write-up, we would write a single paragraph. I broke it up into smaller paragraphs just so we can see where each of the element takes place. So the first thing I have is my narrative sentence. College admissions officers wanted to find out whether applicants' high school GPA was a good predictor of success in college. My second part names where my sample comes from and a little bit about the sample size. I say that I used simple linear regression, and it revealed that the high school GPA was a significant predictor. And that phrase, a significant predictor, is the place where I convey to my reader that I did reject the null hypothesis. And then I report my F-test statistics in APA format. I need to have the name of the test, so it gives me the F for which distribution I'm using, the degrees of freedom for the numerator, which is our systematic component, and for the denominator, which is our error component. I report the actual F statistic, and I always report the actual p-value if I possibly can. That lets my reader know exactly what the likelihood would be of getting a result like this by random chance. I go on, because I had a significant result, to interpret the slope of the regression line and say that a 1-point increase in high school GPA predicted that college GPA would increase by 0.7039 points. I also need my measure of effect size. I know that my R-squared is 0.4671. That's almost 0.5, which would be half. So I use the language of nearly half to help the reader who may not understand my statistical language so much. I say nearly half of the variability in first-year college GPA was predictable by the high school GPA, and then I do report my regression R-squared results. And then finally, I close with another sentence that sums up what I found out. The college admissions officers had evidence to support their use of high school GPA as a criterion for admission. Our textbook dips its toes into the waters of multivariate analysis for a second time with the module on multiple regression. We saw when we studied factorial ANOVA earlier in the course that it was possible to have two variables as a predictor, and that we would be able to test the effect of one variable while controlling for another. In analysis of variance, we also got interaction effects computed automatically. In multiple regression, we're testing for one variable controlling for the impact of other variables, but we would have to explicitly put in the interaction effects. This is really the threshold to multivariate analysis. where we consider the impact of several variables at one time. This is the way that models are built, and in fact, most of the research that's actually carried out is multivariate. If you think of almost any disease characteristic or any mental health state or any economic state, there always are multiple causes, and we really could not explain most diseases or most physical conditions with just one variable. Things like gender or age are almost always part of the picture, as are other physical conditions. So usually when you're reading research, you're going to be encountering multivariate results. It's good to know something about how they work, but it's beyond the scope of this course to get into all of the various multivariate methods that exist. In summary, we can say that regression is an exact expression of the linear relationship that we first saw in correlation. Regression predicts a y value for each x value. The analysis of regression tests whether this line is a better predictor than we would get by random chance, and it also lets us compute the effect size from the sum of squares. The slope that's describing the predicted change in y for a 1-unit change in x lets us understand how the two are related, and the regression equation itself predicts the new values. We saw that multiple regression and factorial ANOVA are both a gateway into more complex statistics, but they are beyond where we will go in this first course in statistics. You have reached the end of all the statistical techniques that you will learn in this course. Module 40, the last one in your textbook, presents you with some charts that have two purposes. The first is to help you choose the right statistical technique when you're doing the computations. Equally important, those same charts help you evaluate when you're reading statistical research whether or not the researchers used the most appropriate technique and whether they did so completely. While it's rare, there are times that researchers use entirely the wrong technique and still somehow make it into print, and other times when they may not have carried out all the steps that you would expect, perhaps forgetting to compute an effect size. So in studying Module 40, I encourage you to think of yourself as both the researcher and the consumer of research. Congratulations on learning this vast array of statistical techniques.